The multiplexer is the most frequently used combinational building block. You use it when you have several signals and need to select one. In this video, I'm going to show you how a simple multiplexer works and how to use CMOS transistors to make fast, scalable multiplexers. Here is the multiplexer. There are two inputs, A0 and A1, and the select bit. When the select bit is 0, input 0 is passed to the output. You can see that when I toggle the A0 input, the output also toggles. And when select bit is set to 1, then A1 is passed to the output. The logic of this is that Y is equal to A0 when the select bit is false, or it's equal to A1 when the select bit is true. And we can see that reflected over here in the logic diagram. Y is equal to A0 ANDed with select bar, or A1 ANDed with select. And again, observing the logic diagram, when the select bit is 0, A0 is propagated through the AND gate and the OR gate to the output. And when the select bit is 1, A1 is propagated through to the output. The number of transistors required for this multiplexer, of course, can be economized by using NAND gates instead of AND and OR. And then this 2-input NAND requires 4 transistors, 4 transistors, 4 transistors, and this inverter requires 2 for a total of 14 transistors. And then, when you consider the propagation delay through the multiplexer, when you change the input, you have to propagate through 2 gates to get to the output. So there are 2 layers of logic and 2 gate delays from a data input to the output. We can make the multiplexer faster by exploiting an important property of MOS transistors. So let's review how the MOS transistors work. MOS transistors come in 2 flavors, the P channel and the N channel. They each have 3 terminals, source, drain, and gate. The P channel transistor is on when the gate voltage is lower than the source voltage. If the gate voltage is greater than the source voltage, then the transistor is off. The complementary transistor, the NMOS transistor, operates in the opposite way, that when the gate voltage is higher than the source voltage, then the transistor is on, and when the gate voltage is lower than the source voltage, the transistor is off. Now, these properties of the transistor have important implications for how the transistor is able to switch. So let's look again at the PMOS transistor. When the gate is lower than the source, if the gate is low and the source is high, then the transistor is on, and that means that there's a connection through the channel of the transistor and the drain is also high. So when the gate is low and the source is high, the drain is high. But under any other circumstances, if the gate is low and the source is low, then the gate is not lower than the source, it's the same as the source. And if the gate is high, then it cannot be lower than the source. And in those 3 situations, the transistor is off and doesn't pass anything. The drain is just sitting down here floating. Now, if you look at the complementary transistor, the NMOS transistor, when the gate is higher than the source, the gate is high and the source is low, then there's a connection from the source to the drain through the channel of the transistor. So the gate is high, the source is low, and then the drain is low. So we say that the transistor passes a 0 from the source to the drain. But in any other combination of gate and source, the gate will either be lower than the source, which turns the transistor off, or the same as the source, which also turns the transistor off, and again, the drain is floating. So for each of these transistors, the PMOS transistor will pass a 1, the NMOS transistor will pass a 0. Now we can combine those two transistors together to make a switch. So here is the PMOS transistor and here's the NMOS transistor. If the control input is low, then the gate of this transistor is low and the gate of the PMOS transistor is high, and both transistors are off, and the output is just floating. It's not connected to anything. It's like a switch that's open. If the control input is high, then the gate of the PMOS transistor is low, the gate of the NMOS transistor is high, and now, depending on what the source is doing, either one or the other of these transistors will be on. If the input here is low, if the source here is low, then the NMOS transistor will be on because the gate is higher than the source, and there will be a path through here. The NMOS transistor will pass a 0, and there will be a low. So the switch will be closed. Okay. On the other hand, if the source is high, now this transistor will be, the NMOS transistor will be off, but the PMOS transistor will be on, and there will be a path through the PMOS transistor to make the output high. So that these two transistors connected like this act as a switch. When the control input is low, the switch is open, and when the control input is high, the switch is closed, and whatever is presented at the source is passed, the common source connection is passed through to the drain. And it's called a CMOS transmission gate. So here is a circuit over here with two of those CMOS transmission gates, one here and one here. And there's an inverter to guarantee that the two transistors are driven oppositely to each other. Let's see what happens when this thing operates. So I'm going to set this bit, which is called the select bit, to 0. So when the select bit is 0, let's see what happens. The select bit is 0, this is low, this comes around, this is high, and this is low. So these two transistors are shut off because the PMOS transistor here has a high gate and this NMOS transistor has a low gate. So this transistor is out of the picture. Whereas this transistor has the gates set up exactly in the right way. And if we toggle input 0, you can see that it propagates right through the transmission gates to the output. But if I toggle input 1, it doesn't, you can see it stops right at the transmission gate because this switch is open and the output is just floating. If I change the select bit to a 1, now it's the opposite situation. There's a high here, and a low, and a low, and a high. So now this transmission gate is off, and this transmission gate is on. And as I toggle input 0, now you can see input 0 gets stuck and never makes it through the transmission gate, and the output is floating, whereas I can toggle input 1, and it passes through. Because one of these switches always has a floating output and the other switch has an active output, it's either high or low, I can tie the two together and that makes a multiplexer. So let's see what happens over here. We'll set the select bit to 0 and we'll toggle input 1 And as you toggle input 1, nothing comes through. If I toggle input 0, the output is 0. If I change the select bit to a 1 and I toggle input 0, nothing gets through. But if I toggle input 1, the output follows input 1. So this circuit is in fact a 2-to-1 multiplexer. And observe two important features of it. One is it only requires 1, 2, 3, 4, 5, 6 transistors instead of 14 for the gate level multiplexer. And the propagation delay from an input through a switch to the output is very fast, much faster than 2 gate delays. So this multiplexer is smaller and faster by virtue of using the CMOS transmission gates rather than AND and OR gates.